Tragedy strikes in the heart of downtown New Orleans.
Oh my God.
The building's collapsing. What? The building's collapsing.
It was really just jaw-dropping.
In North Carolina, a catastrophic bridge collapse on a college campus.
There were some workers on the bridge, under the bridge, around the bridge. There was a failure, and the bridge collapsed.
Devastation in Denmark as a 60-ton tower is destroyed in seconds.
It went so fast that it looks like an explosion.
And in Houston, a billion-dollar bridge goes disastrously wrong.
If there's one little flaw in the bridge, you could have just an absolutely catastrophic situation.
With big builds, even the smallest mistake can be a huge disaster. From miscalculations to misunderstandings, some with deadly consequences. These catastrophes are every engineer's worst nightmare. When it comes to big engineering, planning is key to all construction. Any deviation, no matter how slight, can result in major catastrophe. Like this construction disaster in downtown New Orleans.
I just saw a building collapse, people trying to escape and people running.
Hotel destruction on a catastrophic scale.
Something happened here that was shocking.
A tragedy that left a city demanding answers.
How could a routine build go so disastrously wrong?
New Orleans, Louisiana's biggest and boldest city, is a destination with its own distinct identity. Local journalist Autumn Caffiero-Giusti knows all about this good time town.
New Orleans is a city that's just really like no other. It's very European, very Caribbean. The culture here is different. We're not a quiet city. We like to have fun. You know, it's a place people want to come to because it's an exciting place to be. It's got its own personality.
This charismatic city is a tourist hotspot.
The city welcomes millions of visitors every year who spend billions of dollars. In the Big Easy, big tourism equals big business.
It's one of our primary economic drivers. Our hotel industry is very important to the city. We rely on that hotel traffic and those tourists to really keep the city's economy moving.
In February 2018, construction began on a new $85 million hotel. On the edge of the famous French Quarter, this 18-story structure would break with tradition.
In this part of town, strict zoning laws normally limit buildings to around 21 meters. But this hotel would stand proud at 58 meters.
Professor of Civil Engineering and native of New Orleans, Dr. Norma Jean Mattei explains.
Typically, any structure within the French Quarter is very, very zealously guarded, but that part of Canal Street had not seen as healthy and robust an economy. So the city was looking at how in the world are we going to help develop this area that ultimately became the Hard Rock Hotel.
The plan was for the first 7 floors to house everything from parking to retail, with hotel rooms and private apartments occupying the next 11 stories.
The first 7 floors were reinforced with concrete, and then above that was a frame that was structural steel. So 2 different methodologies.
On the edge of the French Quarter and the business district, this was the perfect location for a hotel to breathe new life into this once iconic part of New Orleans.
With construction well underway, in July 2019, Amaris and Jordan Herndon thought they had found the perfect spot for their new restaurant, just a block and a half from the hotel.
Tourism drives the city 10 months out of the year. There's nothing that was going to be bad about having a massive hotel there.
On October 12, 2019, Amaris was on her way to the restaurant to open up.
It was a Saturday morning. I was driving about 2.5 blocks from here. I'm sleepy, I've overslept, and was running a little late.
More than 100 people were on the hotel construction site, working the weekend shift too.
I'm rushing, and I'm like, the building's collapsing. What? The building's collapsing.
Caught on another driver's dash cam. At around 9 a.m., without warning, the side of the hotel collapsed.
Oh my God.
People, like what looked like to me like rappelling off of the building as they were trying to escape, and people running. Sorry.
The top floors of the 18-story hotel were decimated as tons of concrete and steel cascaded to the streets below. Local journalist Autumn Caffiero Giusti heard the catastrophic news.
Seeing the site for the first time, I've covered disasters before, and I've seen a lot of tragic scenes. This was like nothing else I'd seen. It was really just jaw-dropping.
2 massive cranes were left swaying over the wreckage, forcing an immediate evacuation of the surrounding area.
I was almost a little afraid because the building was so unstable. They didn't know if it was going to collapse more. It was a really sobering scene.
18 people were injured in the disaster, and sadly 3 workers lost their lives.
The collapse was absolutely horrible. The 3 lives that were lost, and if it had happened at any other day, at any other time, the loss of life would have been more significant.
The collapse hadn't just destroyed a hotel, it had destroyed lives. The city and its citizens wanted to know, how could this have happened?
From the footage, you can clearly see the top floors on the street side collapse on themselves first. Then the side toppled over. The big question was why?
The initial health and safety report by OSHA suggests design flaws may have affected the structural integrity of the upper floors, including the 16th story being under-designed in what's known as load capacity. Professor of Engineering Norma Jean Mattei knows strength in any building is key.
When you're building a tall structure, every single bit of that structure, the roof all the way down to the ground, has a load. And that load has to have a path down, ultimately, to the ground.
It appears that miscalculations left the steel connections unable to carry the necessary load, on top of which the concrete floors may have been poured thinner than originally designed.
On the plans, the metal molds for the concrete were around 7.5 centimeters deep, but in reality, they were found to be just 5. That's a very significant difference.
The strength of steel and concrete weren't the only concern. Some questioned the method of construction, specifically in temporary supports or bracing known as shoring.
Shoring is typically used when you're pouring an upper floor of fresh concrete, and so the floor below it is carrying that load through these braces. And so when the floor that you just braced has gained enough strength, you can then remove the braces and use them on the next floor.
To allow the concrete to fully harden for maximum strength, the design specifications required these braces to remain in place for a minimum of 15 days. But some accounts claim that most of the posts were gone after 8 days, just before the building collapsed.
The higher the floor, the younger the concrete, which means the concrete is weaker. It'll fail, fall on the next one, it'll fail, and that caused a series of cascading failures that ultimately took down a whole side of the structure.
Whatever the underlying issues were, ultimately the structure just wasn't strong enough to support its own weight. While the exact cause of the collapse is under investigation, there's no doubt the disaster shook one of the greatest cities in America to its core.
What happened and how it happened. There's a bunch of litigation underway, but something happened here that was tragic, and people lost their lives here.
With the structure still unstable and in a busy part of town, a decision had to be made about what to do with the wreckage.
A typical implosion is where you understand the condition of the building. In this situation, you don't know its condition. You know it's damaged, you just don't know how damaged.
In time, it was decided that the only safe option was to demolish the hotel piece by piece, no matter how long it took. And finally, it's beginning to look like there's light at the end of the tunnel.
I think people want to have normalcy again and, go back to New Orleans, getting to be its usual lighthearted self without having this overshadowing it.
Maybe for some, life can, at last, return to normal.
We were open 3 months before that happened. It's now been a year and a half, and I want to be cleared of that.
New Orleanians, we're resilient, but having the building cleared out and having this street open is going to be a really good day.
When it comes to designing huge structures, engineers need to know their materials inside and out. Get the calculations wrong and it can lead to catastrophe. Like this tragedy in North Carolina, a disaster that devastated a college campus.
There were some workers on the bridge, under the bridge, around the bridge. There was a failure and the bridge collapsed.
Not one, but 2 bridges came crashing to the ground.
Something went wrong when the first bridge went down, but to have the second collapse, it wasn't just a fluke. You don't expect an accident like this to happen.
This double engineering mistake had devastating consequences.
Raleigh, North Carolina, is known as the City of Oaks, and over the years has grown from a tiny acorn into a metropolis. Thanks in no small part to its world-class academic institutions. Local reporter and former newspaper editor Richard Stradling explains.
Raleigh has evolved from this small, sort of southern state capital into a pretty diverse and prosperous city. Education is a big part of what Raleigh is and what has made Raleigh what it is today. To attract the companies and the employers here, if it wasn't for the universities and the colleges that were here, that wouldn't have happened.
It's one of the fastest growing cities in the US, home to 10 universities and colleges, and it's also part of one of the most prestigious research parks in the US.
Raleigh's also home to the state's largest community college, Wake Tech.
The first campus opened in 1963. It had just a few dozen students. And now it's got half dozen campuses across the county, close to 70,000 students.
As Wake Tech grew in student numbers, it needed to expand in size, constructing several new buildings and a parking garage on its northern campus. To connect the garage and campus, in 2014, construction began on 2 pedestrian bridges, crossing the woods and ravine. In keeping with the college's ethos, the bridges would embrace their surroundings. Department of Labor Commissioner Scott Mabry explains.
Wake Tech had decided to build these 2 bridges in place with the laminate wood support. With the setting, you can kind of see the trees and the creek back here. So it was a good blend, I think a good look for the area.
Both bridges would be constructed using huge timber girders, crossing suspended spans over their surroundings. The walkways would be steel beams supporting a metal deck with concrete poured over the top.
During the process of designing a bridge like that, you have to take into account ability of the wood to support the desired load that you're looking for. So the bridges were initially designed to do that, using the wood product in place.
This pair of bridges shared the same construction material. Both would feature a super-strength engineered wood known as glue-lam. Material expert and associate professor of engineering, Dr. Reze Ferron, explains.
So over here, I have a sample of glue-lam, and glue-lam stands for structurally glue-laminated timber. And its name is exactly what it sounds like. You have timbers that are bonded together with an adhesive, a glue. With respect to glue-lam, you can engineer the product such that pound for pound, that it could actually be stronger than steel.
But by selecting glue-lam, engineers faced a design challenge.
One of the disadvantages of glue-lam is that if you have very long spans, you're going to have to, think about how you're going to connect it.
They were shipped across country and brought to the site. So they had to be short enough to be able to ship by truck, and they were put together in pieces.
The glue-lam girders were notched at each end, then pinned together using a metal plate to hold them in place. For added strength where they joined, they would be supported by V-shaped steel columns anchored to the ground.
Anytime a bridge is designed, safety is the #1 factor, and then you try to put the project together in such a way that it may blend in with the surroundings, so you're going to look for the aesthetic at that point. But regardless, safety is going to be the forefront.
November the 13th, 2014, construction of both bridges was well underway.
Bridges were already in place, so they were actually pouring the concrete for the walkway on the top of the bridge.
At around 10:30 a.m., disaster struck.
Suddenly, there's a crack, and the first bridge collapsed.
The entire central span of the first bridge fell into the ravine. There was no warning and no chance to escape.
The bridge dropped around 7.5 meters, taking 5 workers with it. Department of Labor Commissioner Scott Mabry was on the team that immediately began to investigate.
When we arrived on the site, one of the bridges had already collapsed. The other one was under construction, and there was some work activity going on that bridge at the time. So our folks recommended to the contractor at that time to cease activity on the second bridge.
While work was immediately shut down, local newspaper editor Richard Stradling knew a major story was unfolding.
There were students here, so when you hear that a bridge goes down on a campus like this, we had to scramble people up here pretty quickly.
The super-strength glue-lam girders lay splintered on the ravine floor.
We didn't know what had happened here. We couldn't get close, we couldn't see it. We didn't necessarily understand all the engineering, but it was pretty clear that something had gone wrong.
Worse was to follow. Just hours after locking down the site, bridge number 2 collapsed.
Something went wrong when the first bridge went down, but to have the second bridge of the same design at the same stage of construction to collapse, obviously you could tell something was wrong with the bridges. It wasn't just a fluke with the first one. But the second one collapsed shortly after midnight. Nobody was here, nobody was hurt. Very fortunate.
Not everyone was so lucky. Of the 5 workers who were on the first bridge when it collapsed, 4 were seriously injured. Tragically, 1 lost his life. The devastating collapse shocked faculty and students alike. The question was, what had gone so terribly wrong? Inspectors first considered the pouring of the bridge decks.
The bridge had been put in place. The concrete was partially poured on the bridge already, and there was an additional pour that day, which started to add the additional weight, which precipitated the crack along the beam itself and ultimately caused the collapse.
While this might have been the trigger, investigators knew that this wasn't the root cause of the disaster.
For both wooden bridges to collapse within 24 hours of each other, clearly something was fundamentally wrong with either the design or the construction.
Investigators turned their attention to the split glue-lam girders, specifically how they were joined.
The glue-lam product of the bridge was notched at the end where it was on the support column when it cracked laterally down the length of the beam. And that's where the failure occurred. So you could see how the bridge essentially split apart along the laminated section of the bridge.
The notches had created a weak spot that was now subjected to unexpectedly strong forces. Associate Professor of Engineering Dr. Reze Ferron explains.
What ended up happening is that there was already shear forces being applied to the bridge during construction, and then cracks start from the shear forces, and those cracks were horizontal.
The original design for the bridge did not include creating notches at the end of each girder, and for good reason.
One of the issues with putting notches into a material is that when you put a notch into it, you're taking out some of that material. So I think intuitively we can all think, okay, that's going to make it weaker. The other reason why you don't necessarily want to put notches in is because as you put a notch in, what you're doing is creating what we call the stress intensity. So the stresses at the cracked tip of the notch is going to be amplified.
There's nothing fundamentally wrong with cutting notches in wood, it's done all the time. But these were huge pieces carrying heavy loads, so it was essential that they were properly reinforced.
There's additional ways to put threaded rods through the beam itself to hold it together, and that wasn't done, and ultimately contributed to the failure of the bridge.
The weak spots created in the notches at both ends of the girders caused horizontal cracks to form at the column. As more and more concrete was added, the cracks spread further until the weakened wood could no longer take the strain and the whole bridge came crashing down.
The notch was actually the cause of the failure of both of the bridges.
The bridges were designed to easily carry the load of the concrete and the pedestrians. But adding these notches meant that both bridges were destined to fail. It was simply a question of when.
After the disaster, the collapsed bridges were dismantled and removed. However, Wake Tech still needed a solution to keep its campus on the move.
Wake Tech went back to the drawing board and they put in a steel-supported metal suspension bridge out here, and they fit into the environment pretty well. Maybe not quite as nicely as the wood-sided bridges would have, but they do look good, and they do get quite a bit of use.
Today, the two new bridges safely carry students and their teachers across the northern campus and the ravine.
Given the foot traffic here on campus, the incident could have been much worse if it were a nice sunny day and there were 100 people on the bridge at the time. Who knows how bad it could have been.
And the Wake Tech bridge collapse continues to serve as a reminder to the engineers of the future.
One of the things I tell my students is that as engineers, we need to make sure that we understand construction practices as well as our materials, as well as our structural calculations. You can design the best building, but if no one can construct it, it's not going to matter.
From the longest bridges to the tallest towers and everything in between, engineers are in a constant battle with the forces of nature. Any weakness can be exposed without warning. Like this fail in Denmark, which span out of control.
This wind turbine was almost 20 stories high, but it came down in seconds.
The disaster exposed an industry-wide weakness.
It really shows what the wind is capable of.
Engineers were left reeling. Just how had this happened?
It went so fast that it looks like an explosion.
Wind energy. It's clean, free, and vital to our future. Once basic and inefficient, wind turbines have come of age.
Modern wind turbines are truly state-of-the-art, And although the concept is simple, the engineering behind these things is highly complex.
Sandwiched between the North and Baltic Seas, Denmark was an early pioneer in wind energy. Stefan Jorgensen is a local journalist.
Denmark is one of the leading countries in wind energy, and we have been setting up windmills since the 70s, first on the land side and in the recent years also on the sea.
Key to their success is a reliable supply of wind.
Denmark is a quite flat country, and as you can see, there's water around Denmark and everywhere, so there are quite a lot of possibilities to set up windmills in Denmark.
The Riso research station, run by the Technical University of Denmark, or DTU, has been at the heart of the wind industry for 40 years. And it's where Professor Martin Hansen battles the elements.
The wind turbines are very important for Denmark. This is where the first wind turbines were tested and certified before they were allowed to be erected.
The now familiar three-bladed layout became known as the Danish concept. But whatever the name, wind turbines work the same way.
The blades essentially take energy from the wind, turning a gearbox connected to a generator, creating electricity.
The first thing we need to do is to slow down the wind. That means a wind turbine must create a force that is opposite the direction of the wind, and that stops the wind and steals kinetic energy from the wind. We can create this by applying 3 rotor blades here that are shaped as airfoils on an airplane.
These blades aren't just shaped like aeroplane wings. They essentially are wings and fly through the air.
When the wind approaches this airfoil here, comes in with an angle here, it accelerates around this, we call it the leading edge, and that creates a suction. So this blade are actually sucked forward. So the higher is the wind speed, the more is the lift, and the more power we can create.
The faster the blades fly, the greater the forces acting on them, which is perfect for making power, but it puts massive stress on the structure.
On a day where it's not a particularly windy day, actually there is around 100 tons of air passing this area per second, meaning that to stop that, you really need very, very large forces. We have to be very careful when we build these wind turbines.
The forces involved are so strong that every turbine has multiple braking mechanisms to stop them from spinning too fast.
It's required actually that you have an aerodynamic brake on all wind turbines. If we lose the torque from the generator, then there's no torque to stop the rotor. So it spins faster and faster and faster until it reaches a free running speed that creates large loads that may lead to failure. So to prevent this, there used to be a tip brake, meaning that we can turn the blade so that it actually acts like a brake.
The wingtip brakes would deploy, increasing air resistance to control the spin until other systems could slow the rotor.
Wind turbines are everywhere now, so it's easy to forget the technology is still evolving, and it hasn't all been a smooth ride.
On February the 22nd, 2008, a 60-ton turbine in northern Denmark was rotating much faster than usual. A local resident started filming. Journalist Stefan Jorgensen was living nearby at the time.
I remember that day back in 2008, this wind turbine just got spinning out of control for quite some time, and it looked dramatic.
With the wind getting stronger, the 30-meter blades continued to accelerate, exceeding 700 kilometers an hour.
The police already had made a perimeter for about 500 meters.
The turbine span like this for more than 2 hours.
If the brakes were working, it would never have reached that speed, or spun for so long. It was clearly out of control.
At the end, exploded, or what looked like an explosion. It really shows what the wind is capable of and how big the forces in the wind is.
The shattering machine hurled debris in all directions. Luckily, no one was hurt, but the entire turbine was completely destroyed. With turbines like this spread across Denmark, the government launched an investigation.
Denmark is at the cutting edge of wind energy, and these machines are packed with safety systems. So how could something so destructive have happened?
Professor Jens Sorensen was on the investigation team.
That day, they had registered that there was a problem with the mechanical brake, which is located inside the nacelle. So a service team arrived in the morning, and they start to look at that brake. They fixed it.
Having fixed the problem, engineers restarted the turbine.
The wind was very strong, so to keep the rotor under control as it restarted, engineers deployed the air brakes at the tip of the blades.
What you do is you activate these air brakes that you have here, so you can run it up in speed without it starts to run too fast. So you can, so to say, control the speed.
But things were soon far from controlled.
They heard some noises from the gearbox, and they knew there was a problem. And suddenly this gearbox simply blocked the rotation of the wind turbine.
The gearbox failed, instantly stopping the rotor, tearing the air brakes from the blades.
The rotor simply stopped to rotate. These air brakes, because of inertial forces, so they simply broke off.
The loss of the gearbox and air brakes explains why the turbine was spinning so fast. But what caused it to self-destruct?
So it was, while running so fast, it was subject to very, very strong forces. So it starts to bend, and at a certain point, one of the blades simply more or less exploded. And then you have two blades left, and when this happens, then they start to vibrate heavily, and one of the blades went into the tower and broke off, and everything broke off. It went so fast that it looks like an explosion. But if you go pinpoint into small details, you can see exactly what happened. So it's probably the worst accident that ever happened with a wind turbine.
One obvious question was whether the service team had made a mistake. According to Jens and the investigation, that was not the case.
It's a combination of many different accidents happening at the same time, so it's very unlikely it would happen. It's a mechanical error. There's no evidence that it's a human error.
No one could have predicted the gearbox would fail, ripping the air brakes off. With such huge forces at play, the turbine was doomed.
The catastrophic failure did, however, reveal that existing brake systems were flawed.
The accident caused people to question the safety of wind turbines, but Denmark was relying on them for a greener future, so things had to change.
One thing was for sure, the movable blade tip air brakes had to go. The smart solution was to make the whole blade the brake.
Today you have a pitch motor here that can actually turn the whole blade. But also we can use them as brakes, because if you pitch the whole blade so that it's 90 degrees out of the wind, then the whole blade acts like an aerodynamic brake. And thus such a thing as happened on the Hornslet can never occur on such a wind turbine.
This catastrophe was caused by an unpredictable chain of events. But engineers also spotted a flaw in the system, and in fixing it, they helped improve the entire wind power industry.
The outlook of Danish wind power and wind turbine in general is actually very, very bright. Wind turbines and wind energy will just keep on growing.
Some epic structures go wrong after the construction teams are long gone. But others fall early in the game. Like this mammoth construction project in Texas, a vital link brought to a grinding halt.
There's one little flaw in the bridge, and you could have just an absolutely catastrophic situation.
This project barely got off the ground.
The independent reviewer said that the settlement calculations were quite a bit off.
I think what we can say about this bridge is that Houston, we have a problem.
Houston, Texas, established around sluggish bayous that drain into Galveston Bay and the Gulf of Mexico. Local transport journalist Gail DeLaughter knows what makes Bayou City tick.
Houston is America's 4th largest city in terms of population. There's parts of the city that are very urban, other parts that sort of have a rural character about them. This is also part of the city of Houston as well, the refinery activity and the industrial activity.
One waterway is crucial to the city's industrial success, the Houston Ship Channel.
Literally billions of dollars in economic activity every year comes through the Houston Ship Channel, and there's a lot of development all along the route.
About a century ago, the Ship Channel was the sluggish, swampy Buffalo Bayou. But engineers have transformed it into one of the most important waterways in the U.S.
Civil engineer Matt Yarnold is heading out to get a bird's-eye view of this essential waterway.
The Port of Houston is a big economic driver for the region. It's responsible for about $265 billion to the economy of Texas, as well as employing over 1 million people within the state. What they say about Houston, it was the town that built a port, which built a city. So the port itself is a big factor for the size of the city and the tremendous growth of the last 100 years.
As industry drove a population boom, bridges sprung up to cross the channel. One of the most important is the Sam Houston Ship Channel Bridge, which opened in 1982 to carry the city's Beltway 8 toll road over the water.
So out my window here you can see the existing Ship Channel Bridge. It's actually a segmental concrete box girder bridge built roughly 40 years ago. It's actually in excellent condition, but the bridge itself is rather narrow.
With just 2 lanes in each direction, the bridge was struggling to meet rush hour demand.
You have the usual vehicular traffic, the people who live here, but then they're on the roadway competing with a lot of trucks that are coming in and out of the port.
The city needed more capacity, and in 2018, construction began on a brand new 8-lane bridge. But it wasn't going to be cheap.
The price tag for the new bridge is about $1 billion. It's the most expensive infrastructure project that Harris County has ever undertaken.
The epic price tag would buy an epic bridge like no other, with unique curving pylons over 150 meters high, towering above the twin road decks, in a design known as a cable-stayed bridge.
Basically, there'll be large pylons or towers that are going to come out of the riverbanks, and major steel cables will come off it, which will support the deck system below. So you can see in the background here, you can see the pylon just coming out of the ground adjacent to the bridge.
The eye-catching design isn't just good to look at.
The cable stay design allows for a longer and higher main span than the old bridge, giving more clearance for the ship channel below, while the twin decks double the amount of road bay.
The new bridge will actually have 4 lanes in each direction with much wider shoulders, so the traffic capacity will be greatly increased.
The project is as ambitious as it is unique.
A bridge of this scale has a number of challenges, both from the design side as well as construction. Building towers 500 feet off the ground is no small feat, in addition to a structure that's spanning well over 1,000 feet.
But the biggest hurdle engineers faced with the whole project was getting the old bridge out of the way. This billion-dollar bridge faced a million-dollar question.
The existing bridge can't be closed until the new one is built, and yet it stands exactly where half of the new bridge needs to go. The solution was pretty audacious. Essentially build it like 2 bridges.
The new bridge is being built parallel to the old bridge. The intended staging is to build the first half, switch traffic from the old bridge to the new bridge, and then demolish the old bridge and then build the remaining half of the new structure.
With construction well underway on the first half, the project hit a major setback.
They started working on the bridge in 2018, and then they did a design review about $400 million into this project, and they found about 21 different structural problems that would have to be dealt with.
With alarm bells ringing, city planners hit the brakes.
They decided to just go ahead and shut down everything on the bridge, all the construction on the new bridge, until they can figure out what to do about those design flaws.
You don't shut down work on a project like this without a good reason. Something must have gone badly wrong.
Close inspection revealed that 3 key elements of the design were flawed, starting with the foundations, which would settle more than expected.
Settlement is exactly what it sounds like. The weight of the structure causes it to sink a little.
Settlement is vertical movement of the foundation. As you impart significant loads onto the soil, in this case it is on pile foundations, which will minimize some of the settlement, but if the structure then goes downward and then of course moves the components and parts of the structure, which can induce stresses and other issues into the bridge.
Every new structure settles up to a point. But if it goes further than expected, it can have serious consequences.
In this case, the independent reviewer said that the settlement calculations were quite a bit off, which would affect the remaining stages of construction.
Settling wasn't the only problem. The review found the design didn't fully account for sideways or lateral forces.
The lateral loading is critical when designing a structure like this. The 2 primary lateral loads that we account for in bridge engineering is seismic loads and wind loads.
Houston has never suffered an earthquake, but wind loading was one of the key factors in this bridge design, especially in a hurricane hotspot like Houston.
The critical components are where the deck system attaches to the vertical element known as a pylon, so you can have excessive stresses and potentially cracking in this region, as well as those forces need to be transferred all the way through to the foundation, so you can have other points of stress and concern, and even down into the base of the structure.
As well as having soft foundations and being vulnerable to strong winds, there were also concerns about the main cables supporting the bridge deck.
The independent design reviewer questioned the slip resistance of the main cables. That's essential because if you can imagine, all the main cable system is in significant amount of tension, and if you were to release and have a slip and release that tension, that force is then transferred into the surrounding cables.
Any problem with the cables would have a domino effect throughout the entire structure.
If you can imagine live load such as this, imparting a vertical force downward on the structure, it's going to put tension into the main cables, and it's going to impart a compressive force in the deck system. All these tensile forces are then pulling on this vertical element known as a pylon, which then puts it into significant amount of compression and then forces everything into the foundation.
There are so many massive forces constantly at play on a structure of this size that every detail, from the cables right down to the foundations, has to be absolutely right.
And with more than 100,000 vehicles a day projected to cross this new bridge, even the smallest imbalance could have disastrous consequences.
With $1 billion and potentially thousands of lives on the line, engineers were left with no choice but to put the brakes on the entire project.
It is crucial to take care of these things at an early stage because just imagine if there's one little flaw in the bridge, it leads to another flaw, it leads to another flaw. You could have just an absolutely catastrophic situation.
With such fundamental problems, new designers were brought in for a fix. The new team came up with a series of retrofits that will be built onto the already completed bridge sections. Crucially, all the potential dangers have been ironed out.
It is a good thing that they found these things in advance, one for public safety as well as for the long-term performance of this particular structure. Had this not been uncovered and been uncovered after the fact, the situation could potentially be much worse and, of course, more costly.
No matter how beautiful that bridge is, if it's not built to serve its purpose, it's useless.
With the new plan in place, Houston no longer has a problem and hopes to have its trailblazing new crossing open to traffic by 2025.